heaters, or we call heaters or furnaces, that are pieces of equipment used in processing facilities such as in refineries, power plants, petrochemical complexes, and others. And it is used to heat fluids up to the desired temperature. So the main purpose of fire heaters is to raise the temperature of the processed fluid that flows through the tubes. The heat energy is supplied by combustion fuels. However, there are also numerous problems that affect the safety, reliability, or environmental performance of fire heaters. The acidic stack emissions limits on NOx or CO as well as cooking is frequently a problem in fire heater. These two factors have a big impact on how well a fire heater works. When we not overcome it properly, several issues can appear. Therefore, we have included the solution for these problems. Now let's go through the problems first.
Assalamualaikum, my name is Imran Faiz. I will be explaining on two major problems of fire heated refinery. Okay, one of the major problem is that it is exceeding stack emissions limit on nitrogen oxide and carbon monoxide. As we all know, many of these chemicals leave the facilities as an air emissions, wastewater, or solid waste. Typically, this type of material or waste is what we call it volatile organic carbons, carbon monoxide, sulfur oxide, and nitrogen oxide. And we will be focusing on two major waste, which is carbon monoxide and nitrogen oxide. What is nitrogen oxide and carbon monoxide? Carbon monoxide is made out of one molecule of carbon and one molecule of oxygen, which is held together by a triple bond. Another thing is which is nitrogen monoxide. It is a colorless toxic gas, which is formed by oxidation of nitrogen. Why is it a problem to us? Is because it is a problem to a human itself. It has no problem to the environment, but it is very harmful to the human because because if humans get access of a lot of nitrate oxide, it will cause a lot of respiratory ailments such as hematologic side effects, and some of them low blood pressure and even worse, death. And if carbon monoxide, which usually will be a carbon monoxide poisoning. The next major problem will be the excess coke in fire heater. Heater cooking in crude and vacuum distillation unit is a common occurrence for many refiners. To deal with this kind of occurrence, some refiners need to be shut down for every 2 years, some maybe 1 year, or even worse, every 6 months. What is coke actually? Coke is formed because conditions in the shock or radiant tubes cause the oil to thermally decompose to coke and gas. Rapid coke formation is caused by the combination of high oil film temperature, long oil residence time, and inherent oil stability. You can see it through the picture that I have put inside the slide. One of it is the first picture on the top, which has some kind of a carbon. What we call it carbon, but it's actually we call it a coke. Why is it a problem to the refiners? Is because the coke deposit can lead to insufficient heat transfer and also flux constriction, and it requiring to shut down of all the equipment in order to remove the coke, despite the coke deposits inside the tubes. So it is quite time consuming to clean out all the cokes inside the tubes, because first thing, the tubes are very big and the tubes are connected to some of the tubes are connected to the whole facility, so it's quite hard for them to repair and to clean the coke. That's all for me.
Many refinery vacuum furnaces have problems in cooking, even at mild operating conditions, and we use steam to inhibit coke formation in various ways. As Imran said just now, rapid coke formation is usually caused by the combination of high peak oil film temperature. So steam injection is one of the best options for lowering the film temperature, because steam able to reduce the oil residence time by increasing the fluid velocity. high fluid velocity improves heat transfer in the film layer, which lowers the differential temperature between the tube wall and the bulk fluid. Besides that, steam is utilized to passivate the coil surface before the introduction of the feed by exposing the coil to high temperature steam for several hours. Under these conditions, the synthesis of catalytic coat is delayed and prevented by the accretion of chrome oxide layer. However, for other coils that have been repeatedly depuled and have a rough surface, this procedure performs less well. The tube coating application process prevents scale formation and oxidation from the tube surfaces for the duration of the coating. High emissivity ceramic coating is then applied, which prevents any further oxidation and scale growth for the life of coating. The high emissivity nature of the coating ensures that a maximum amount of radiant heat available is absorbed by the tube surfaces. Besides that, the efficiency of radiant section heat transmission can increase by as much as 15% when high emissivity coatings are applied to refractory and tube surfaces. Therefore, two important effects on NOx and CO2 emissions result from this improvement in heat transfer efficiency. Its lower temperature of the flue gas leaving the radiant area.
Direct steam injection is the most widely used method for boiler feed tank heating throughout industry. This method is often chosen because of its simplicity. No heat transfer surface or steam trap set is required, and there is no need to consider the condensing heater system. Heat is transported differently during direct steam injection than it is during indirect heat exchange. Because steam freely mixed with the processed fluid being heated, heat is not transported across a surface. Steam injection uses a portion of the liquid enthalpy present in the steam as well as all of the enthalpy of evaporation or latent heat. The actual amount of liquid enthalpy consumed will depend on the water's temperature following the injection operation. The rate of steam consumption and the amount of heat required are directly connected. The steam bubbles may simply break the surface of the liquid and escape to the atmosphere if the steam injection system is not designed to ensure that all factors are favorable for maximum heat transfer. In this case, some of the heat contained in the steam will be lost to the atmosphere and the actual heat transfer rate to the water will be lower than anticipated. In the case of a submerged coil, the maximum heat transfer rate at the start of the warm-up period will depend on the maximum steam flow rate allowed through the control value and its associated pipework, and the maximum heat output allowed by the coil surface area. It always advisable to ensure that the temperature of the liquid is correctly controlled and is kept to the minimum required for the application, so that the maximum heat transfer rate is maintained and there is no waste of energy. When the radiation from a flame strikes a perfect radiator, all of the energy is absorbed, but most importantly, it is transformed into black body radiation as the white wave band form. As the energy is re-emitted from the surface, it can penetrate the atmosphere in the furnace, composed of the combustion products, with little being reabsorbed and taken to the stake by the draft. Therefore, it is more readily available to heat the load in the furnace. If the surface were a poor radiator or one having a very low emissivity value, the energy striking the surface will be reflected from the surface still in its untransformed state, therefore more readily absorbed by the furnace atmosphere. The effect is to superheat the furnace atmosphere or flue gas, resulting in wasted energy lost to the stack. Naturally, a reduction in flue gas temperature follows an increase in radiant heat transfer efficiency. This has an impact on how heat is transferred. Convective heat in the fire heater's radiant and convection section. The convection section uses heat from the flue gas to create steam, as well as to preheat the combustion air and frequently to process fluids. To make sure that the balance is not negatively impacted, it is important to carefully evaluate the heat transmission and absorb duty balance. Lower temperature leaving the radiant section bridge wall temperature, since more of the available heat is absorbed by the process tube in the radiant section. In higher temperature process such as catalytic reforming, steam maintenance reforming, and steam cracking, the NOx emission reduction has been found to be as high as 25 to 30%. The increase in radiant section heat transfer efficiency means that the same absorbed duty may be achieved from the use of less hydrocarbon-free which could lead to 15% reduction in CO2 emission. The higher emissivity ceramic coating have been successfully used in more than 200 catalytic reformer applications. Due to the fire heater configuration, relatively high heat flux and process outlet temperatures in this type of unit, they have proven to be excellent candidates for ceramic coating application, which more typically see around 7% efficiency improvement, leading to even better payout and ROI result.
For the conclusion, the steam injection system is not intended to ensure that all factors are optimal for heat transfer. In this case, some of the heat contained in the steam will be lost to the atmosphere, resulting in a lower than expected heat transfer rate to the water. To ensure that the balance is not harmed, balance of heat transfer, the heat transmission and absorb duty balance must be carefully evaluated. And the last part is that it is very important to have a good design of fire heaters, as it will be beneficial to industry in the long run. Benefits could include improving efficiencies, reduce emission, increase heater and cube life, and consistent product qualities, and the lastly is optimum throughput. And I think this is all from us, from our group, and I hope you enjoy our video. And Assalamualaikum, that's all from us.